Hi everyone, welcome to this new lecture of hydraulic machines. In this lecture, we'll discuss a new concept regarding unit quantities of turbines. In the unit quantity of turbines, we'll consider a few parameters or which are the most important parameters in these unit quantities. These are speed, discharge and power. First, we'll try to understand why this unit quantity of turbine is required to study. The thing is, when you predict or when you try to identify what is the performance of a turbine or to the behavior of a turbine, and because we know that the turbines are working in different conditions will be there, like the turbines are working in different heads and under different speed, and similarly in under different you can say gate openings, different gate opening valves you can say, and similarly in different outputs also sometimes it will be worked. So these are the many parameters are there under where the turbines are working. So to identify it or to understand the behavior of a turbine when it is working in different conditions, so finally what will give this turbine? The output will given like in terms of quantities. The outputs will come from here like a quantities will be there, some value will be there, and that can be identified or can be obtained in terms of like when the turbine will consider in under single head or unit head, we can say the head need to be considered as a unity, so that we can able to calculate or we can able to identify the behavior of these other turbines. And this unit quantities, why it is required also I can say when we are talking about the behavior and characters. So suppose an engineer is there and he or she needs to design or to calculate that which is the best one or which turbine is the best one for which kind of heads, because as I told you that it will work under different heads. So the engineers can easily compare and can easily analyze the turbines performance of different sizes and even different operating heads also, so that it will help an engineer to identify which is the best turbine for different heads and different applications also. So now we'll see, as I told you that unit quantities, some important parameters are there, important unit quantities are there like speed, discharge and power. So we'll discuss one by one. So first one I'll consider the unit quantities, unit speed. The first one I'll consider, that is unit speed. So first one is unit speed. So unit speed is actually it is defined as the speed of a turbine when it is working under a unit head. Yeah, one more thing, as I told you unity, that means we need to test these things or we need to identify the performance of these things under unit head. Unit head means one single head, 1 meter. Okay, so the unit speed we can write here, the speed of the, so speed of the turbine, we can say suppose speed of turbine is working, the speed of turbine is working under unit head or single head, we can say. We need to do like this, unit head. Let's find out for unit head, then we can go for different heads also, we can calculate that. And the unit speed is denoted by NU. The N is for speed and NU is the unit speed. So to calculate or to identify these things, we need to consider some other parameters also. Like as I told you, this is NU is defined for the denoted for the unit speed. Similarly, N is the speed of the turbine. We know that N is the speed of the turbine under it's a head. This is H is nothing but head under which the turbine is working. Similarly, we need to consider small u. This is tangential velocity. Capital V. This is absolute velocity, or you can say the jet velocity also. Similarly, Q is the discharge, and finally we can go for like power. So these are some terminology we need to remember. Okay, to find out this value, we need to consider first U is proportional to, we can say, V. Why? Because I can say you two formulas, like we know that V1 or V is equal to we know this equation CV root over of 2GH. So if I write this equation in terms of like V1 or V, suppose let's put V1, suppose V1 is proportional to 2gh. Now in this equation, if you see 2 and g both are constant, and now we can write here v1 is proportional to root over of h. Similarly, another one equation we have, like if you remember the flow velocity and like speed ratio and flow ratio, in that terminology we can write in this way. Again, we know that u also, or u or u1 we can write this is equal to like ku root over of 2gh. Ku actually equal to u by root over 2gh, that I have written in this way. So here also I can write like u is directly proportional to root over 2gh, and similarly I can write u is proportional to root over 2gh. So u and v both are proportional to each other. So though it is in this way also I can write. So here what I'll mention here, u is directly proportional to h here, and this one let me give an equation 1 suppose. And now the tangential velocity also, this u, as I told you, tangential velocity, this also we can write u equal to, we know the formula, like pi dn by 60. Now if you see this equation, in this equation this is pi is constant and n is constant, and this is 60 value is constant. Now okay, here actually diameter is constant, not n, so you can consider, yeah. So this constant value you can take it out. So diameter suppose fixed is there. Now here I can write u directly proportional to n. Okay, u is directly proportional to n, and here what we got, u is directly proportional to h. So from this we can write, here n directly proportional to root over of h. By this equation and this equation we can write n is directly proportional to h from these two equations. And now if I write this, extend this value, and if I write, then this one we can write in this way, like n equal to, just remove this proportional symbol and just multiply one constant. This is k1 root over of h, and this k1 is nothing but here, this is constant of proportionality. This is constant of proportionality, we can write. This is constant of proportionality. Okay, and yeah, this is one equation what we got here. Now as I told you that we need to consider a unit head, we need to calculate the speed of turbine, means we need to consider it should be run under a unit head. So if head of the turbine become unity, that means h is single, and to find out the value of n, then we can put one value like h equal to 1 meter we can say, and put the value of n, speed equal to nothing but specific unit speed. Okay, so we can write this equation. This equation will become like nu equal to, this is k1 and this is root over of 1. So we can write finally this is nothing but nu equal to k1, correct. Now the same value, what I'll do, the same value I'll just put in the equation. Okay, this equation where we got this, like this one you can give equation number 2. Now put the value in the equation 2, then we can find out what will get the value here. N equal to we can write nu, just put the value of this constant here, how much how nu value. So nu, and this is root over of h. We need to find out our unit speed, so we can write unit speed nu equal to n divided by root over of h, or else we can write this is nu equal to n by h to the power 1 by 2. This is another one equation, we can mark it here. This is our unit speed. Similar way we can calculate for the unit discharge also. Okay, to calculate the unit discharge we need to go for the, like, okay, I'll tell you what need to consider. So this is the first one. The second one, as I told you, that unit discharge. In the unit discharge also we need to define the unit discharge will be, we can say the discharge passing through a turbine, which is working under a unit head. Same thing, which is working under a unit head. So it's the same thing what I have told you, like a speed of turbine is working under one unit head. So here also the discharge of the turbine, or discharge passing through the turbine under a unit head. So the unit head is need to be considered to calculate this unit quantities. That means 1 meter or unity need to be considered for all these conditions. So similarly for this one, we know that what is the formula of Q. So Q equal to, we know that AV. Okay, we know that AV. So in place of AV, I can write also here, this is suppose Q. Q is directly proportional. I can write because area, if you see here, AV in area equal to, area is constant because diameter is constant. So area can be taken constant. Now area is constant means we can write Q is directly proportional to V. Q is directly proportional to V. And if you see in our last equation where we got this V is directly proportional to root over of H. And so here also I can write same thing. This Q is directly proportional to root over of H. And here again I can just put the value of Q and I'll just write a constant K2 and this is root over of H. Now similarly here also I can write this K2 is nothing but constant of proportionality. This is constant of proportionality. Okay. Now again we need to find out the value of K2. Same process need to be done. Now here also we need to consider that H equal to, as I told you, unity, that means 1, and the discharge we need to consider unit discharge. This is Q. Yeah, Q is the symbol for unit discharge I have mentioned. Okay. Now here again we just put the value in this equation, this one. Then what we'll get here on behalf of Q, let's put it QU, and this is nothing but K2 and root over of 1. So we got the value, this is QU equal to K2. Okay. Now this is suppose equation number 4. Just put this value in the equation number 4. We can get here, no, not this one. Actually, this is, yeah. Okay, correct. This one, equation number 4. Now we can write here, this is our Q equal to, what is the value of K2? That is QU. So QU and root over of H. Now we can write this is QU because our requirement is to find out the value of unit discharge, that is QU. So we can write this is Q by and root over of H, and also we can write this is Q by H to the power 1 by 2. This is our equation 5. So this is the value of unit discharge. Similarly, again the same thing, unit power. Unit power is nothing but again same thing we can define, like it can be defined the power developed by the turbine. Power developed by the turbine under a, which is working under a unit head. Same thing, which is working under a unit head. And this also will be denoted by PU. And this can be like how we can find out this unit power. We need to consider the efficiency. Which efficiency? Now the overall efficiency. Overall efficiency equal to, we know that power developed, output will be there. That is nothing but the power developed. And what is the input will be there? Now what is the water power is there? This is short power or water power. Short power by water power we can say, or we can say that is water power by, power developed by water power. So power developed nothing but we can mark it as a P, and water power we can give it, we know the formula, that is rho G QH by 1000. Rho G QH by 1000. Our requirement, you need to find out the power term. So what I'll do, I'll take this power term one side and remaining term to the other side. So I can mark it here P, and remaining terms, as I told you, like I'll take it to the other side. So that is your eta naught into, this will be there like rho G QH by, here we'll get the 1000 value here. Now, if you see this equation, in this equation, how many constants are there? So that we can take the remaining parts. So this 1000 constant, this is constant, and efficiency, this will be also here constant term. Remaining what are the terminologies are there? That is P now directly proportional to Q into H. Okay, directly proportional to Q into H. Now previously we have seen that Q is proportional to root over of H. Just put the value here. So you can write P proportional to Q into, in the place of, sorry, not Q, here we need to write root over of H. So P directly proportional to, on behalf of Q, I can write root over of H into H. If I write this one, then again I can write here P is directly proportional to H to the power, this is 1 by 2, this is 1. If I add these things, we will get 3 by 2. This is 3 by 2. Okay. Yeah. The next is, we can write this is P. I'll just remove this proportional symbol so that I can write P equal to, this is K3 H to the power 3 by 2. This is another one equation. We can give equation number 5 or 6. Yes, 5 already given. So I can mark it equation number, suppose 6. Now again same procedure, we need to find out the constant of proportionality K3 value. So how to find out? Now we need to consider when unit head I told you, that means H equal to 1 meter and P need to be considered as a unit power. Then just put the value in this equation. Then we can get here PU equal to K3, and this is 1 to the power 3 by 2, nothing but we'll get only K3. So we got the value of PU equal to K3. Just again put the value in this equation. So what we'll get here, like P equal to, this is PU H to the power 3 by 2. But what is our target? I told you that we need to find out the unit power, unit discharge, unit speed. So I'll keep this PU one side and remaining terms other side, like P by 3 by 2. This is our unit power. Okay, and this one we can give equation number 7. But the previous one I have given equation number 6, this one I can give equation number 7. Now what is the use of this, all these quantities? Already I told you that the use of, or the application of unit quantities, why we are studying this one. Again I'm telling you, the use of these quantities, the unit quantity is nothing but, suppose the turbine is working on single head. Single head means okay. If it is working in different heads, then different behaviors of the turbine can be easily identified by these values, by these equations. So what equation we got here? The same thing if I tell you, like suppose unit speed is there. Now unit speed, we know that, we know one formula, only one, that is N1. Suppose this is for one head. Okay, for first turbine, I can say this is for one turbine. So what I can write, N1 by root over of H1. If it is multiple turbines are there, how to compare this like different turbines? So I can write this equal to, I can write N2 by root over of H2. So this H1, H2 are the heads under which the turbine is going to work. Okay, this is one term. Similarly, I can write this is the discharge, unit discharge is nothing but, I can write same thing like Q1 by root over of H1, and here I can write this is Q2 divided by root over of H2. Similarly, here also same thing. We need to consider that Q1 and Q2 are the discharge of the turbine in different heads. The last one, what I can write, PU. PU is nothing but same thing I can write. This is P1 by, what was the formula was there, like 3 by 2, and another one the turbine which is head of a different turbine. So this one will also you can write H2 to the power 3 by 2. So if you see, these are the two different turbines I have taken. You can consider multiple number of turbines also, like H3, and you can consider also discharge Q1, Q2, Q3, Q4, different turbines, different heads, and different speed and power and discharge can be calculated. So by using this relation, the speed, discharge and power that can be calculated but same turbine under different heads. Okay, turbines are like same, but different heads are there. Here H1, here H2. Again, we can go for H3. So turbine will be same, can be considered, but different heads can be taken and can be calculated. These are the terminologies. So why this final one? Let me tell you conclusion it. So the performance, the overall use of this unit quantities, we can compare the performance. Already I told you, we can compare the performance of turbines. We can compare the performance of turbines, and we can design. We can design and we can select also. We can design and select the turbines also, which turbines is required and which turbine need to be selected. Okay, and that scaling from the model prototype. So model prototype can be done, and we can do the scaling for that model prototype, and scaling also can be taken, can be done. And also I told you, like we can calculate different behaviors. We can identify or we can calculate different behaviors under different head conditions. Under different head conditions. We can write here under different head conditions. So these are the use of unit quantities. Also I told you in the starting also, like why this unit quantity is required to study for specifically a turbine case. So I hope you understand this derivation and this theory part, like the unit quantities of turbine in terms of speed, discharge and power. We need to remember that we need to consider only unit head or unity. If you are having any kind of doubt and query regarding this, you can give a comment on the comment box. Thank you all.